So, welcome to this. This is lecture number 21 of the course on fundamentals of transport processes. We had in the previous few lectures first looked at dimensional analysis and correlations and how these dimensional correlations are derived in different situations for the dependent variable, that is the non-dimensional flux as a function of a set of independent variables, which are ratios of convection and diffusion, different types of diffusivities, and where applicable interfacial forces, inertial forces, gravitational forces, and so on. And we had looked in some detail at the diffusion process itself. How is it that diffusion takes place? Okay. There are two broad categories of transport. One is convection, which is due to the mean fluid flow, and that convective flux, the flux per unit area, the amount transported per unit area per unit time across a surface, is just equal to the fluid velocity perpendicular to the surface times the density of what is being transported, the concentration, energy, or momentum. Okay. The diffusion flux, on the other hand, okay, is related to the variation of the concentration, energy, or momentum across a surface, and these are given by constitutive relations. They contain a diffusion coefficient with dimensions of length square per time times the gradient, okay, of the quantity of the material of that particular of the density of that quantity, the spatial variation, okay, difference in concentration divided by the distance. Okay. In the limit as the distance goes to 0, this is just the spatial derivative, okay, of the concentration, the energy, or the momentum. Okay. So, those are the two mechanisms, okay, and we were looking in the last lecture at how to apply this to a unidirectional transport problem. Okay. So, for definiteness, what we had was a surface at z is equal to 0. So, we use a coordinate system where the x and y directions are along the plane and z is perpendicular to the plane. So, we had the surface with initially the temperature was a constant everywhere in the fluid, and instantaneously at time t is equal to 0, this surface alone was heated to a higher temperature. Okay. The surface alone was heated to a higher temperature, and we wanted to know how this increase in temperature at the surface is going to heat up the fluid. Note that in this case there is no convection, therefore, there is no fluid flow perpendicular to the surface, therefore, transport has to be due to diffusion alone. Okay. So, we had written down a balance equation. The boundary and initial conditions for this problem were initially T is equal to T infinity everywhere. Okay. Initially the temperature is equal to T infinity everywhere, okay, for T less than 0. At time T is equal to 0, the surface is heated. Okay. So, therefore, for T greater than 0, the temperature is equal to T naught at the surface. Okay. However, since we have considered this as an infinite fluid, far from the surface, the temperature is still equal to T infinity. Okay. And I tried to explain to you that this could be an idealization of a problem where you are trying to heat a fluid in a container. Okay. Initially, the temperatures are constant everywhere, and at time t is equal to 0, you heat up the fluid from the bottom, okay, and therefore, the heat will diffuse up the fluid. This approximation of an infinite fluid is valid when the distance to which the fluid heats up is much smaller than the total height of the container. In that case, this approximation is valid, and we will see a little later, okay, as we go through the course, as we go through this problem, what is the thickness of the fluid layer which is actually heated up. So, we had posed this problem. Change in energy within a time delta t is equal to energy in minus energy out plus the sources of energy, may be due to phase change, due to exothermic reactions, due to endothermic reactions, and so on. Okay. The change in energy within a time t is just equal to the energy, the internal energy of the fluid at time t plus delta t minus the internal energy at time t. Okay. Energy in at the surface z, okay. If you recall, we had a differential volume of thickness delta z, okay, within the fluid. The energy in at the surface z is qz, okay, that is increasing the thermal energy if qz is positive, if the flux is upwards. Energy out is at the location z plus delta z, okay, that is leaving. Therefore, if qz at z plus delta z is positive, the energy within this volume is being decreased. Okay. And that was these two terms, energy in and energy out, plus the source term. Source is a volumetric source, energy added per unit volume per unit time. So, you take this balance equation, divide throughout by volume and the time interval to get a differential equation, okay, for the temperature. Basically, this states that the rate of change of energy within this volume is equal to the net flux, what comes in minus what goes out, a negative sign because what is coming in at z is increasing the energy, what is leaving at z plus delta z is decreasing the energy. Okay. And then you have the source term. In the constitutive relation for the heat flux, qz is equal to minus k dt by dz. Energy is transported from regions of higher temperature to regions of lower temperature, therefore, the negative sign. And when you put that in, you get the balance equation of this form. Alternatively, if I divide throughout by rho Cp, the balance equation basically becomes, okay, a diffusion equation. Okay. dt by dt is equal to the diffusivity times d square t by dz square plus the dimensionless source. Okay. One can define an exact analogous problem for mass transfer. The surface, initially the concentration of some solute is 0 everywhere or C infinity everywhere within the fluid. At time t is equal to 0, you instantaneously increase the concentration on the surface, okay, to C naught, and then you want to see how the concentration evolves. The equation is the same once again, change in mass instead of heat. Okay. Change in mass within a time delta t is equal to mass in minus mass out plus sources. You get an equation for the concentration field in terms of the spatial derivative of the mass flux Jz. Okay. Jz is the mass flux in the z direction. It has exactly the same form. dC by dt is equal to minus the derivative of the flux with respect to z plus any sources or sinks of mass due to reactions, or and then you have to put in the constitutive relation. The flux is equal to minus d times dc by dz, and from that you get the concentration diffusion equation. dc by dt is equal to d times d square c by dz square plus the sources. All of these assume that the diffusivities are independent of position. Okay. In general, if the diffusivities do depend upon position, the correct equation is actually d by dz of d dc by dz plus s. Okay. If the diffusivities do depend upon position, the diffusion coefficient does have to come within one of the derivatives. Okay. Similarly, if the thermal diffusion coefficient was dependent upon position, then the equation which will actually be rho Cp or rather, okay, if the density and the specific heat do depend upon position, the equation will be of the form d by dt of rho Cpt is equal to d by dz of k dt by dz plus the source. Okay. So, that is how the equation would look if the thermal conductivity and the specific heat were dependent upon position. When these are independent, if these are constants for a fluid, you will get the diffusion equation. Okay. So, We had solved this for momentum transfer as well. Okay. In that case, we had considered a surface, a fluid adjoining a surface, an infinite fluid. Initially, everything was at rest, and at time t is equal to 0, the surface was moved instantaneously with a velocity u. Okay. So, for t less than 0, the velocity ux is 0 everywhere, and for t greater than 0, ux is equal to capital U at z is equal to 0. Far from the surface, the momentum diffusion has not yet happened. Okay, if you go to a large distance from the surface, how large we will see once again, but if you go to a large distance from the surface, since momentum diffusion has not yet taken place, the velocity still has to be equal to 0. We had framed the problem slightly differently in this case. The rate of change of momentum is equal to the sum of the forces acting on that fluid element of thickness delta z. Okay. So, the rate of change of momentum is equal to the sum of forces. Forces are of two kinds: surface forces, which act on surfaces, and body forces, which act toward the entire volume. Okay. Surface forces are the shear stress, the momentum diffusion across the surface. Body forces are forces like gravitational force, centrifugal force, and so on, which depend upon the volume of the fluid. So, the gravitational force exerted in a volume is proportional to the volume itself. Okay. You increase the volume, the force is higher. Okay. So, you had two forces, the surface forces acting on the top and bottom surface, and the volumetric forces. Okay. And on that basis, once again, there was an intricacy here regarding the sign convention. We had defined the stress as positive if it acts at a surface whose outward unit normal is in the plus z direction. Note that the stress tau x z, okay, momentum in this case is a vector. Okay. It has the momentum itself has a direction, okay, the direction of the force, okay, and there is also a direction of the surface, the direction of the transport. Okay. The force itself is in the x direction, the transport is taking place in the z direction. In other words, the z coordinate is the direction perpendicular to the surface across which the transport is taking place. So, the stress will have two indices. The first one, the direction of the momentum. The second one, the direction in which the transport is taking place, or the direction of the perpendicular to the surface across which the transport is taking place. In this case, the velocity is in the x direction. So, the direction of momentum transport is the x direction, and the direction in which the transport is taking place is the z direction. Okay. So, those were the two indices in the expression for the momentum transfer, in the expression for the stress. We had assumed a positive sign when the z direction is in the positive direction for the top surface, and negative when it is in the minus z direction. The shear stress itself has a positive sign. So, the equation that you get for the velocity field turns out to be exactly the same form as the equation that we had for concentration and energy diffusion, except that instead of the mass, the concentration or the temperature, we have the velocity. Instead of mass diffusion or energy diffusion, we have momentum diffusion or the kinematic viscosity. And this equation will be the same for all unidirectional transport problems. This equation was a balance that was done for a particular differential volume within the fluid. Therefore, the form of the equation does not change if you change the configuration. Okay. If you had an infinite fluid instead of a semi-infinite fluid, or if you had a fluid between two plates so that it was in a finite domain, this equation was written for an internal volume, and therefore, that is going to remain the same independent of configuration, so long as transport is taking place only in one direction. I should also note here that momentum transport in fluids contains the additional complication of pressure. In this case, we have not assumed any pressure differences or pressure gradients. We assume the pressure is a constant everywhere. How does one treat situations where there are pressure gradients is something that I will come to a little later when we do the effect of pressure on fluid flows. Okay. So, we have these equations and how do we solve them? Okay. I will solve it for the case of the temperature field, and by analogy I will just write down the solutions for the concentration and momentum fields. Okay. So, the equation, I have a situation where this is the z direction, z is equal to 0 is at the surface. Okay. At the surface t is equal to t naught, okay, and far from the surface t is equal to t infinity. Okay. So, if I plot the temperature field, okay, depending upon how long time has elapsed since I have heated the bottom surface, the temperature field will decay from this value of T naught, okay, to T infinity, okay, in some manner. Okay. If I plot the temperature as a function of cross stream position, okay, perpendicular to the surface. Okay. So, my equation is, okay, let us assume for the present that there are no sources or sinks, that the heating is entirely due to the heating of the bottom surface. Now, this temperature changes approximately from T naught to T infinity. Okay. Rather than using a dimensional temperature, it is more convenient to use a scale temperature. Okay. Rather than the temperature going from T naught to T infinity, I could scale the temperature so that the temperature far from the surface is just equal to 0. Okay. That is easy to do. Okay. I could write down a scale temperature as T minus T infinity divided by T naught minus T infinity. Okay. So, whereas I have in this picture I have T naught here and T infinity here. Okay. If I were to plot the scale temperature, you can see that far away it is equal to 0. Okay. At the surface itself, T is equal to T naught and the scale temperature is equal to 1. Okay. So, if I were to plot on this axis T star instead of T, okay, it goes from approximately 1 to 0 far away. Okay. So, I am just scaling the temperature, okay, that is all. Okay. And this is convenient because even though the solution for the temperature T does depend upon the values of T naught and T infinity, once I have scaled it, the solution for T star is independent of the values of T 0 and T infinity. Okay. And expressed in scaled form, you can see that the temperature dimensions on the left and the right side of the equation are the same. This is a linear equation in the temperature, okay. And therefore, the equation just becomes dT star by partial T is equal to alpha partial square T star by partial Z square. Okay. And the boundary conditions at Z is equal to 0, T star is equal to 1. Okay. I showed you that Z is equal to 0, T star is equal to 1. As Z tends to infinity, T star is equal to 0, and at T is equal to 0, that is when we have just increased the temperature of this bottom plate. T star is equal to 0 for all Z which is not on this bottom surface. Okay. At T equal to 0, we have just initiated the heating. T star is equal to 0 for all Z greater than 0. At the surface itself, T star has become equal to 1 because we have instantaneously heated the surface. Okay. So, now we have scaled the temperature field. Okay. Can we scale the time and the length? Okay. What are the time scales in the problem? What are the length scales in the problem? Okay. If you recall, if we had a finite channel, we would have had a length with which we could have scaled, okay, the Z coordinate. If it were a channel or a pipe or something of finite dimension, we could have scaled the length in this coordinate. This configuration is of infinite extent. Okay, this configuration is of infinite extent, and therefore, it is not possible to find either a length scale or a time scale. Okay. Time goes from 0 to infinity, length goes from 0 to infinity as well. Okay. So, it is not possible to find a length scale or a time scale. Okay. So, there is basically a deficit of dimensional quantities in this particular problem. Can one get a dimensionless group involving the length and time? Okay. What are the parameters we have in this problem? We have z coordinate, we have time, and we have the thermal diffusivity. Okay. So, out of these three, can we get a dimensionless group? Okay. Since the diffusivity has dimensions of length square per time, there is only one dimensionless group that you can get, okay, from these three, okay, is equal to z by root dt. Okay. Because of a deficit of dimensional parameters, we cannot find separate dimensionless groups involving length and time. Okay. There is only one dimensionless group that we can create. I put the mass diffusivity here, my apologies, it should be in this problem the thermal diffusivity. Okay. We can get only one dimensionless group, that is the ratio of the z coordinate and square root of alpha t. Square root of alpha t you can see easily has dimensions of length. Okay. So, in this problem, if I were to express both time and z in terms of this parameter psi, which is dimensionless, I should get an equation which contains nothing else, okay, a dimensionless equation which contains nothing else. Okay. This thing is a procedure that is called a similarity transform. Just based upon dimensional analysis, I can reduce the partial differential equation in two variables, time and z, into an ordinary differential equation which is only a function of the scaled coordinate psi alone. Okay. So, this basically reduces the partial differential equation to an ordinary differential equation. You would recall earlier when I had discussed the formulation of equations, I had said that in the case of partial differential equations, there is no systematic way, there is no algorithm which will enable you to find a solution. A solution may exist, a solution may not exist. In most of our solution procedures, what we will try to do is to use physical approximations to reduce this partial differential equation to one or more ordinary differential equations. This physical insight in the present case is the realization that because there is a deficit of dimensional variables, we can reduce the length and the time coordinates to just one dimensionless variable. And if what I have done is correct, the equation that I get should be only a function of psi, it should not individually be a function of z and t. Okay. So, how do I do this reduction? I can write partial t by partial t, okay, is equal to using chain rule for differentiation, and my postulate at this point is that t is only a function of psi. It does not depend individually on z and time, but only through this combination. Okay. So, therefore, in this case I can write this as just a total derivative. Okay. And I can integrate and I can differentiate this. I will get z by 2 root d t to the 3 halves, okay, partial t by partial psi. Okay. And z by root dt is psi itself. Okay. So, I will get psi by 2 t. Okay. Okay. I should have a negative sign here because in this case t is in the denominator. So, when I take the derivative I get minus 1 by 2. Okay. So, I should have a negative sign here. So, that is for the temporal derivative. The spatial derivative is going to be equal to, I should use alpha here instead of d. No negative sign here. Okay. And the square root is on both. Okay. So, I take the derivative of psi with respect to z here, I just get 1 over root alpha t. Okay. When I take the derivative of psi with respect to z, I just get 1 over root alpha t. Okay. Taking the second derivative, you will just get one more factor of 1 over root alpha t. So, I just get 1 over alpha t times partial square t by, this is a total derivative because t is only a function of psi. Okay. So, now we put that into the conservation equation, okay. And what I get on the left side is minus psi by 2 t dt by d psi is equal to the thermal diffusivity into 1 over alpha t d square t by d psi square. Okay. And now you can see that the thermal diffusivity cancels out on the right side, and the factors of 1 over t cancel out on the left and the right side, and indeed I do get an equation which is only a function of psi alone. Okay. So, the equation that I get is d square t by d psi square is equal to minus psi by 2 dt by d psi. Okay. So, that is what my equation reduces to in terms of the variable psi. Okay. It is not enough to write down the equations in terms of the similarity variable psi. One has also got to express the boundary conditions in terms of the similarity variable psi. Okay. So, z is equal to 0 implies that z is equal to 0 implies that psi is equal to 0, okay, when z is expressed in terms of psi. Z is equal to infinity implies that psi tends to infinity, okay, because psi is z by root alpha t. The initial condition, okay, initial condition at t is equal to 0, at t is equal to 0, the similarity variable is equal to z by root alpha t. So, for all z greater than 0 at t is equal to 0, this similarity variable is psi goes to infinity, okay, because if t is equal to 0 and z is greater than 0, psi tends to infinity. Okay. And you can sort of see that I had two boundary conditions here, z is equal to 0 and z tends to infinity, and one initial condition, t is equal to 0 in the original problem. In terms of the transformed problem, these two have reduced to identical conditions in terms of psi. Okay. That is required for consistency. Initially, I had a first order differential equation in t and second order in z. So, I needed two conditions in z and one condition in t. The transformed equation is only second order in psi, and therefore, there are only two conditions in psi. Therefore, two of the conditions that I originally had should reduce to the same condition when expressed in terms of psi, and that has happened correctly. This means that my similarity transform is correct. Okay. So, we have posed the problem in terms of a similarity variable. Okay. The next task is to solve this equation, and that is always possible because in this case this is an ordinary differential equation and we can actually get a solution and then find out how the temperature varies with time, how the fluxes vary with time, and so on. So, how do we solve this? We will continue that in the next lecture. I will see you then.